In question number 15, we have a current in a conductor and potential difference are measured by an ammeter and a voltmeter. So we used a ammeter and a voltmeter to find out the current flowing across a conductor. But there is a zero error in the voltmeter, and because of this zero error, it will give a little error compared to what's the actual voltage. And then we found that there are two different readings in the circuit, and these two readings are pair of these readings are 1.75 ampere and 14.4 volt and 2.75 ampere and 22.4 volt. And we need to find out what is that zero error. So typically the circuit looks like something like this. Let's say we have a battery connected something like this, and because of this battery, when we connect it, there's a current flow in this direction, and we get a meter reading, ammeter reading, and a voltmeter reading. Now the zero error is something looks like this. The meter reading reads 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but when it should be 0, it's not 0, it's a little bit, let us say, it can be beyond 0, or it can be on the positive side, or it could be negative side from the 0, on the left hand side of the 0. So for the sake of solving this problem, let's assume that it's on the positive side. So there's a positive error. What it means? When, let's say, the meter should have been here after the deflection, it's actually here. So the actual reading is this much, but because meter is a little ahead, it is showing this much. And let us say that error is delta V. Then we are given that under certain conditions we read 14.4 volts. But if delta V was the error, then the actual reading was here. Actually the meter should have been here. Then the actual reading is 14.4 volt minus delta V. And that is equal to, we are given that the ammeter reads 1.75 ampere. So if R is the resistance of this circuit, let us say in this R we have included the ammeter's resistance as well, which stays fixed. So that will be equal to, according to this Ohm's law, 1.75 plus R. Okay, now in the second case we read 22.4 volt, so the actual reading will be less than that because of the zero error. Minus delta V is equal to 2.75 into R. So if we need to solve for delta V. What we do is we need to eliminate Y. So we can divide this equation and get rid of R by dividing it. If we do that, we get 1.75 divided by 2.75 here. And then this can be divided by 25. 25 into 4 is 100. 25 into 6 is 150. So 25 into 7 is 175. And 25 into 8 times is 200. 9, 10 times is 250. 11 times is 275. Multiply 7 by here, 7 by this, and 11 by, take 11 to this side and this whole thing to the right hand side. And then 11 delta V minus 11 delta V goes here, becomes 11 plus 11 delta V minus 7 delta V, it becomes 4 delta V. And on this side we have 14.4 multiplied by 11 minus, this side goes over here, multiplied by 7, then comes back here, becomes 7 into 22.4 and becomes minus 1 here. 11 minus 7 is 4. Now from this 4 we can divide 14.4 and 22.4. 14.4 divided by 4 is 4 into 3, 12, 2, 4, 4 into 6, 24. 22.4 divided by 4, 4 into 5, 20, 2, 4, 4 into 6, 24. 11 into 36 is 396. That is a simple way to multiply by 11. You write this 6 terms and then add these two, 6 plus 3, 9, and then this term. 7 into 6, 42, 2, 4, 7 to 5, 35, plus 4, 39. If you subtract this, this delta V comes out to be 4 plus 0.04. Now, if this delta V would have come to be negative, that means that our zero error is a negative zero error. That means the meter reading would have been on the negative side in the beginning. I hope that this helps.